Okay, so in the first part of lecture, I explained to you that we can use metric approach to estimate parameters of regression model. Okay, so and also I explained how we derive formula that can be used to estimate parameters for regression model that has, doesn't matter how many independent variable it has in the model. Okay, so a metric formulation of the multiple regression model in the multiple regression setting, because of the potentially large number of predictors, it is more efficient to use matrices to define the regression model and the subsequent analysis. Here we review basic metric algebra as well as learn some of the more important multiple regression formulas in metric form. Okay, so I know that you have already learned before about matrix and as well as metric operation, but here we refresh your knowledge how you can use that. That's the reason why you learned before, because you can use that in other courses. So consider the following simple regression function. Okay, given, so we just consider a model that has only two variable y, one y and one x. So this one we call a simple linear regression function. So we actually let I equal to 1 up to n. So we see that we obtain an equation. So as I explained before, so we can, so in this node, okay, it use epsilon to represent the error term instead of u, the one that given what we call in the previous node. So well, that is a pretty inefficient way, as mentioned before, to write. If you want to write one by one, if let's say we have a large number of observation. So as you can see, there is a pattern that emerged. By taking advantage of this pattern, we can instead formulate the above simple linear regression function in metric notation. So we can express the variables or the data in matrix form like this. Okay, so you can see that this is the what we call the matrix for dependent variable, and then matrix X matrix. So because we only have one X in the model, so the first column all equal to 1 for that one for the intercept beta 0, and then we have what we call the values for the independent variable X, and then we have this one vector for parameters. Okay, so we only have beta 0 and beta 1, and then the plus the what we call the vector for or matrix for error term. That is, instead of writing out the n equation using metric notation, our simple linear regression function reduced to a short and simple statement, this one. So now, what does this statement means? Well, here is the answer. So in this case, the given what we call that this one. So x is n times 2 matrix. Y is n times 1 column vector. Beta is 2 times 1 column vector, and the error term epsilon is n times n column vector. So normally what we call that we refer at the matrix dimension, we put or we mention we state the column first, column times number of row. Okay. So x number of row is equal to n. Okay, how many observation, and then it has two column. So n times 2. Okay, so for the other we got the same for the other matrix. So n the matrix x and vector b are multiplied together using the techniques of metric multiplication, and the vector xb is added to vector the error term using the techniques of metric addition. This one you learned before. If you already forgot, I mean you know what we call that, you forgot how to do it, then please refresh your knowledge so that you can use that matrix operation to estimate parameters. Okay, so definition of matrix: n r number of row times c number of column. Matrix is a rectangular array of symbol or number arranged in R rows and C columns. So A matrix is almost always denoted by single capital letters in boldface type. So here are three examples of matrices. So this one times matrix 2 times 2, matrix 5 times 3, and then this one matrix 6 times 3. So it has 6 row, 3 columns. And then dimension of a vector and a scalar. A column vector is nr times one matrix, so that it only has one column. Okay, and then row vector 1 times c, so it has one row, So this one column vector, it only have one column, but this one row vector, it only have one column row. So scalar, it only has one. It only has what we call that 1 times 1, only one value. And then metric multiplication. Okay, so this one you learned before. Okay, two matrices can be multiplied together only if the number of column or the first matrix equals the number of row of the second matrix. Okay. Okay, so this one, I mean, you can read. I leave it to you to read the what we call the explanation. Okay, so this just to refresh your knowledge. This one, the one that you learned before in other course on matrix operation. So this example, so to multiply matrix, you need to make sure that both matrix have what we call that the two matrices have. I mean, for the first one, the number of column for the first matrix must be equal to number of row for the second matrix. Otherwise, you cannot multiply two matrices. And then matrix addition. Okay, two matrices can be added together only if they have the same number of rows and column. Okay, so otherwise you cannot add. So example this one. So this one, it has the same number of row and column. I mean the same dimension, matrix dimension. If with different dimension, you cannot add. This one you just simply add. So for the matrix multiplication before, you multiply. When you multiply row and row of the first column and the second as row of the first matrix at with the column of the columns of the second matrix. For example, this one, a row, the first row multiply the first column in the second. So this one, 1 times 3 plus 9 times 5 plus 7 times 6. So you get 90 and so on. So please refresh your knowledge how to perform multiplication, matrix multiplication. For matrix addition, you just simply add. So this one, this plus this, you get 9. 4 plus 5, you get 9. Negative 1 plus positive 2, 1. Okay, and so on. Okay, so this one, if you express our data in matrix form, you multiply, you get back this one. Okay. So you multiply, for example, for the first one, y1 equal to 1 times beta 0 plus beta 1 times x1 plus epsilon 1. Okay, you get this one. So this the exercise. What must the size and content of the beta matrix beta be in the following equation? So in this case, you can see that we have one column for the intercept, all equal to 1, and then in our x matrix, and then we have 3 independent variable. So meaning that here you need to have beta 0, beta 1, beta 2, beta 3. Okay. All right, least square estimate in matrix notation. This one, we in the first part of lecture, I explained to you how we derive the formula. This formula can be used to estimate parameters, regression parameters, the slope, the intercept, as well as the slope parameters. So in this case, x transpose x inverse. This one is the inverse. This one in the inverse of the x transpose x matrix. X transpose is the transpose of the x matrix. So again, please refresh your knowledge. So do review, go up and review inverse and transpose of matrix. So as I explained here, so this one the transpose example. For the matrix transpose, you just change the what we call that column to be row, row to be column, for example. So this one, for example, this one, and then matrix A. So transpose A is just, so this one columns become row, and then this one second column become the second row. Okay. So this is another example. So X, if you have X matrix, then X transpose this one. Okay. All right, and then definition of identity matrix. This one also you have already learned before. Identity matrix means that the diagonal element equal to 1, but other element equal to 0. Okay, so the square n times n matrix, identity matrix denoted I, n is a matrix which one on the diagonal and zeros as well. Okay, the example for 2 times 2 matrix, identity matrix. Okay, so if any matrix you multiply with identity matrix, then you will get back the matrix. This one. And then the definition of inverse of a matrix. Okay, the inverse, for example, A inverse of a square matrix A is a unique is the unique matrix such that you multiply the inverse and the matrix inverse of A and matrix A, and then you get identity. Okay, so either you, or similarly you multiply A and inverse of A, then you get the identity matrix. Okay, now consider an example. Okay, so now consider example. Let us take a look at an example just to convince ourselves that any least square estimate are obtained by the following metric formula. So so this one, as what we discussed before, we derive using what we call that differentiation, partial derivative. So let us consider data in the table below, which the height of sort in a standard dispan was recorded for various amount of soup. Okay, so using eViews to fit the simple linear regression model to this data, we obtain this one. Okay, so if you open the data given in eViews file, okay, so this one, so so we have the y and x as we call it as defined in the notes. So we have so we want to estimate is in eViews, you estimate using eViews, then you just go to quick estimate equation. So here you have the data y as well as x variable. X and y. Okay, so estimate, you just put y space c space x. So dependent variable y, so c for the intercept, and then you just put what we call the independent variable. So we get this one. So our intercept is negative 2.2685, and then our slope for the x variable is 9.5. Okay, so this one. Okay, so now let us see if we can obtain the same answers using answer, estimate using the both metric formula. We probably showed that x transpose x for the given case, because in this case there is only one independent variable. Okay, so meaning that okay, so for the given example, so we have our y variable, which consists of 7 observation, and then your x matrix. Okay, because there is an intercept, you need to have 1 in the first column, all equal to 1, and then the second column is the values. Is the value for the first independent variable. There's only one for the independent variables. Okay, so the first value, second value, up to the last one. So in this case, for x transpose x, meaning that you x transpose this one, it becomes this one. So x this one, so x transpose x. So you multiply the first row and the first column. Okay, 1 times 1 plus 1 times 1 up to the last one. So it is sum of 1. How many times is n times? Okay, so it is equal to n. N. Okay, 1 plus 1 plus 1 up to 7 times. So it is equal to n. So of course in this case sample size n equal to 7. Okay, and then you multiply the first row and the second column. Okay, so you get sum of x lah, this one. 1 times x, x1, okay, x11 plus x12 plus x13 and so on. So it is a sum of x, or sum of x1, what we call I, because by this one, again, we only have one x. So this one, if you multiply the second row and the first column, you get the same. Okay, and then second row and the second column. So x1 times this one plus x12 times x12. So so it produced the sum of x squared. Okay, because each of these multiply each other the same, what we call the x1i, so that it is x squared, so sum of x squared. So that's how we obtain this one. So x transpose x for the given example, this one, simple regression, then x transpose x equivalent to this one, n. Okay, this one, sum of x, sum of x, this one sum of x, this one sum of x squared. Okay, and then you can identify this one. You can use Excel, for example, to find out or to get what the values for each of these. So n, you know that is equal to 7. Okay, sum of x, then you can just use Excel to get sum of x and then sum of x, x squared. Okay, so you can do that in Excel. So this one. Okay, so you have sum of x, sum of y. Okay, and then to get what we call that x square, sum I square, so you square each of x. So 4 square, 16, 4.5 square, 20.25 and so on. You get sum, so you get this one. So meaning that now, the x transpose x for this example is equal to this one. Okay, so we call this one and 7, sum of x 38.5 and then sum of x square 218.775. All right, and then how about x transpose y? X transpose y. Okay, so x transpose y. So x transpose just like before, and then you have y. So the first row and this one you multiply, you get sum of y I. Second row and this one you get sum of x y. Okay, so you need to compute the sum of y and then the sum of x times y, so that you get what we call that the x transpose y. Okay, so sum of y, this one, 347, and then sum of x, y. Okay, this one, 1975. So we have determined x transpose x and x transpose y. Now all we need to do is to find the inverse for x transpose x. As mentioned before, it's very messy to determine inverse by hand. Letting computer software do the dirty work for us. It can be shown that the inverse of x transpose x is given by this. I mean, it's still possible to compute manually, but when it involves metric dimension higher than 2 times 2, then I mean, it is not what we call that. It is tedious to compute. Okay, so for this one, you refer to the link given in spectrum. Okay, so you can use this formula to compute the inverse of matrix. So for example, for 2 times 2, it's not that difficult to compute. So let's say you have matrix 2 times 2, A matrix like this. Okay, so, so the inverse of the matrix can be obtained using this formula. Okay, so you just, what we call it, compute this one 1 over, if let's say this one, your A matrix, so 1 over AD minus BC, and then this one you change the position, so for D and A, and then you put minus for B and C, and then you get the inverse, the inverse of the matrix. For the case of 3 times 3, then, as mentioned before, that is quite tedious to do, but you're still able to compute it manually, or to find out it manually, or to determine it manually using this, okay, or for the higher dimension. Okay. Okay, so for the given example, given that the x transpose x this one, so you can use the technique just now given by the link in spectrum to compute or to get the inverse of x transpose x, because it is 2 times 2, it's not that hard. So you can just use that what we call that formula, or what we call that I mean the technique to compute. So this one, so you get this one. So this is equivalent to the one that given in the notes. Okay, so we get this one. Or you can just use computer. You can also try to use metric calculator available, the online metric calculator. So please explore. Okay, try to what we call that. There is a what we call metric calculator available online that you can use. Okay, try to use that any of the calculator, then a metric calculator to obtain this one for x, the inverse of x transpose x. So putting all our work together, we obtain the least square estimate. And this one, you use the formula we derived before to get the estimate. So now if you compute this one, you get, you multiply this one x transpose x inverse, and then this one x transpose y. So you get the estimate for the slope and the intercept and slope. This one intercept negative 2.27, and then this one the slope 9.5. Okay, so exercise is one, show that the inverse of this, okay, is this one. So by illustrating that when you multiply the two matrices together, you get the 2 times 2 identity matrix. So this one, if you multiply, try to multiply this and this, x transpose x, and then the inverse of the x transpose x, you should be able to get the identity matrix. Okay. And then the next one is a linear dependence. There is just one more really critical topic that we should address here, and that is linear dependent. We see that the columns of the matrix A are, okay, this one, columns are linearly dependent, since at least, if you consider the example, at least one of the columns can be written as a linear combination of another, namely the third column. This one, the third column, is 4 times the first column. Okay, so if none of the column can be written as a linear combination of the other column, then we say the columns are linearly independent. Okay, so in this case, for this given example, what we call that, the columns of matrix A are linearly dependent because this one, this the third column equal to 4 times of the first column. Okay. So unfortunately, linear dependence is not always obvious. For example, the columns in the following matrix, this one, are linear dependent because the first column plus the second column equal 5 times the linear column. Okay, so now why should we care about linear dependence? Because the inverse of a square matrix exists only if the columns are linearly independent. Since the vector of regression estimate, the estimate B depends on the inverse of the x transpose x, the parameter estimate, the B0, B1, or B beta 0 hat or beta 1 hat, and so on cannot be uniquely determined if some of the column of X are linearly dependent. That is, if the columns of your X matrix that is 2 or more of your predicted variable are linearly dependent, or nearly so, you will run into trouble when trying to estimate the regression equation. So basically, when you have linearly dependent columns in your X matrix, then you cannot, if exactly linearly related, then we do have the problems of perfect multi-collinearity. That one you learned before, multi-collinearity. Okay, and then so for example, suppose some strange reason we multiply the predicted variable. Okay, so by 2 in the data set above, that is, we would have to have 2 predictor variables, say sub1, which is the original, and sub2, which which is 2 times the original variable, the sub variable. So you have 2 independent variables. So let's say this one, you can see that. So this one, your y variable, this one, the first x independent variable, the second independent variable. So you can see that the second independent variable is just 2 times of the first independent variable. So we do have what we call that in your X matrix, so your I matrix for this given example, the first column all equal to 1, and then second column this one. Okay, this one the third column. So it has 3 columns. But the second and the third column linear related. Okay, because we know that the third column is equal to 2 times of the second column. So if you try to regress for this data, we see that EViews will give you this notification. Okay, so let us try in EViews. If you use what we call the Excel, you're still able to produce, but basically the what we call the estimate is not correct. But use EViews, then you can see that. Okay, so let's say okay, we create another variable. Let's say so we have x2, which is 2 times of x1. 2 times of x, because this one we previously just put at x, not x1, x2 equal to 2 times x. So we have x2 here, and then we estimate, and then we add the another variable. Well, we know that x2 is linearly related to x. Okay, so if you estimate this model, you get this notification, so error message. So near sigmoidal matrix regressor may be perfectly collinear. In this case, of course, it is perfectly what we call that related collinear. All right, so that's you get this what we call message, then it means that there is a perfect multi-collinearity. Okay, so in short, the first moral of the story is don't collect your data in such a way that the predictor variable are perfectly correlated. And the second moral of the story is your software package reports an error message concerning high correlation among your predictor variable. Then think about linear dependence and how to get rid of it. So you need to check that sometime you incorrectly, what we call that, mistakenly put or include the variable twice in the model. Okay, let's say you type x1, but you probably you not realize that the one of the variable is just equal. It's just the what we call that the other variable, but you what we call that you mistakenly you incorrectly put the same variable in the model, but you put different name. So you're not aware that one, but you get the that message. So you need to check lah. You need to check maybe there is what we call that perfect multicollinearity because of the what we call it, you incorrectly include the same variable in the model. And then it's also possible that okay, so probably you have already learned before, if you have, let's say you have so in this case you look at the X matrix, the X matrix for this one. Okay, for simple regression like this. Let's say you include dummy variable. Okay, that one we discuss again. There is one topic, but you have already learned before what is dummy variable. So you have, let's say you want to include dummy variable for 2 categories. Let's say you have male and female. Okay, you can create one dummy variable for male, one dummy variable for female, and then if you include that, then the sum of the 2 dummies equal to the first column. Okay, all equal to 1. Okay, because we know that for each observation, each of the individual can only be either male or female. So either it is equal to 1 for the first dummy, or 1 for the second dummy. Okay, so either 1 or 0. So you take sum, the sum of the 2 dummies, all equal to 1. Okay, so that you will get the same error message if you estimate individuals, because there is perfect what we call that collinearity, because the sum of the 2 dummies equal to the first column. Okay, so if you still want to have that in the model, then you need to take out the intercept beta 0 so that you don't have the first column all equal to 1. Okay, but normally we keep the intercept in the model. So in that case, you keep the intercept in the model, then you need to exclude one of the dummy variable. That one we will discuss again when we discuss the topics of what we call that the dummy variable. We do have one topic to discuss on that. Now, for this one, just now, if use, then you get the error message. But if use Excel, I think you still can get result. Estimate, but the estimate is not correct. It's not correct. Okay, so you need to be careful. So maybe we can try to estimate in Excel, not use Excel. Okay, so this is the same data. Okay, so we have X and Y. Okay, so X and Y here. I mean, if you want to estimate using Excel, also can. You can use what we call that this one, data analysis tools. You select regression. Okay, so probably you have learned before how to use Excel to estimate. Okay, so you select Y range, your Y, the dependent variable, and then you have X range, your independent variable. Okay, so just press OK, then you get the same value of estimate, intercept, negative 2.6, and then 9.4, 9.5 for the slope parameter. Now let's say, okay, let us try, um, let's say we mistakenly include the linear related variables. So let's say this one, your x1. So let's say we have x2, which is just like before lah, 2 times of this one. Okay, so let us try to estimate the model. So a regression, so dependent variable is one, and then independent variable. So you have two variables, but they are related, perfectly correlated. Okay. Okay, so you get this one lah. Okay, but I mean it still produce result. It does not give you an error message to tell you that there is a perfect collinearity. So you need to be careful. So you have this kind of what we call that output. So it's possible that indicates for the what we call that present of what we call the perfect collinearity. Okay, but Excel does not give us warning or what we call the message to tell us that there is a perfect collinearity, unlike the one that given by Avius. Okay, so that's how we use matrix approach to perform estimation, to estimate what we call that regression parameters, regression to get the estimate of regression parameters. So, and we use the formula we derive through what we call that differentiation, and then the formula can be used, as I mentioned before, it can be used to estimate a regression model that has any number of independent variable. You just use the same. We can just use the same formula, okay, for any what we call the regression model with any number of independent variables. Okay.